This presentation is delivered by the Stanford Center for Professional Development.
Right. Okay. So, welcome back. What I want to do today is wrap up our discussion on support vector machines. And in particular, we'll talk about the idea of kernels, and then talk about L1 norm soft margin SVMs, which is what will let us apply SVMs even to data that's not linearly separable. Then I'll talk about the SMO algorithm, which is an algorithm for solving the optimization problem that we posed last time. So to recap, right, we wrote down the following convex optimization problem. And all this was assuming that the data is linearly separable, which is an assumption that we'll fix later. And this, but just is this loud enough? Can people at the back hear me? Is this okay? It's fine? Okay. Thanks. And so with this optimization problem, given a training set, this will find, I guess, the optimal margin classifier for the data set that maximizes this geometric margin from your training examples. And so in the previous lecture, we also derived the dual of this problem, which was to maximize this right, alpha I, alpha J. Okay, and this was the dual of our primal SVM optimization problem. Well, here I'm using these sort of angle brackets to denote inner product. So this is just, xi transpose xj, right, for vectors xi and xj. And we also worked out that the weights w would be given by sum over I, alpha I, yi, xi. And therefore, when you need to make a prediction, so at classification time, you need to compute the value of your hypothesis applied to an input x, which is g of w transpose x plus b, right? Where g is that threshold function that outputs +1 or -1. And so this is g of sum of I, alpha I, okay, and so that can also be written in terms of inner products between input vectors x. So what I want to do is now talk about the idea of kernels, which will make use of this property that it turns out we can take the only dependence of the algorithm on x is through these inner products. And in fact, you can rewrite the entire algorithm without ever explicitly referring to an x vector, but only ever taking inner products between input feature vectors. And the idea behind kernels is the following. Let's say that you have some input attribute. Let's just say for now it's a row number. Maybe this is the living area of a house that you're trying to make some prediction on, like whether it'll be sold in the next 6 months. Quite often we'll take this feature x and we'll map it to a richer set of features. So for example, we may take x and map it to these 4 polynomial features. And let me actually just call this mapping, phi. Right? So we'll let phi of x denote the mapping from your original features to some higher dimensional set of features. So if you do this, and if you want to use the features phi of x, then all you need to do is go back to the learning algorithm, and everywhere you see xi comma xj, right, we replace it with the inner product between phi of xi and phi of xj. Right? And so this corresponds to running a support vector machine with the features given by phi of x rather than with your original, maybe one-dimensional input feature x. And in the scenario that I want to consider, sometimes phi of x will be very high dimensional. And in fact, sometimes phi of x, so for example, phi of x may contain very high degree polynomial features. Sometimes phi of x will actually even be an infinite dimensional vector of features. And the question is, if phi of x is extremely high dimensional, then you can't actually compute these inner products very efficiently, it seems, right? Because to compute this, you need to represent an extremely high dimensional feature vector and then take an inner product between them. It seems like that would be computationally inefficient. But it turns out that in many important special cases, we can write down what's called a kernel function, denoted by k, which will be this. Which will be the inner product between those feature vectors. And it turns out that there will be important special cases where computing phi of x is computationally very expensive. Maybe it's impossible. There's an infinite dimensional vector, and you can't compute infinite dimensional vectors. But there will be important special cases where phi of x is very expensive to represent because it's so high dimensional. But nonetheless, you can actually compute the kernel between xi and xj, or you can compute the inner product between these two vectors very inexpensively. And so the idea of the support vector machine is that everywhere in the algorithm that you see these inner products, we're going to replace it with a kernel function that you can compute efficiently. And that lets you work in feature spaces phi of x, even if phi of x are very high dimensional. Okay? So let me now say how that is done. And we're actually, a little bit later today, we'll actually see some concrete examples of phi of x and of kernels. For now, let's just think about constructing kernels explicitly. Right? And then this is best illustrated by an example. So let's say you have two inputs, x and z. Normally, I should write this as xi and xj, but I'm just going to write x and z to save on writing. Right? So let's say my kernel is k of x comma z equals x transpose z squared. Okay? And so this is right? This is x transpose z. This thing here is x transpose z, and this thing is x transpose z. So this is x transpose z squared. And that's equal to that. And so this kernel corresponds to the feature mapping where phi of x is equal to, and I'll write this down for the case of n equals 3, I guess. Right. Right. And so with this definition of phi of x, you can verify for yourself that this thing becomes the inner product between phi of x and phi of z, right? Because again, inner product between two vectors is, you just take a sum over the corresponding elements of the vectors, you multiply them, right? And so if this is phi of x, then the inner product between phi of x and phi of z will be sort of a sum over, all the elements of this vector times the corresponding elements of phi of z. And what you get is this formula. Right? And so the cool thing about this is that in order to compute phi of x, right, so you need order n squared time just to compute phi of x, right? If n if n is the dimension of x and z, then phi of x is the vector of all pairs, I guess, of xi, xj multiplied with each other. And so the length of phi of x is n squared, is order n squared. So you need order n squared time just to compute phi of x. But to compute k, but to compute the kernel function, all you need is order n time, right? Because the kernel function is defined as x transpose z squared. So you just take the inner product between x and z, which is order n time, and you square that, and you've computed this kernel function. And so you just computed the inner product between two vectors, where each vector has n squared elements, but you did it in n squared time. Okay?
For any kernel defined for x and z, do phi exist for x and z?
Let me talk about that later. Right. We'll talk about what is a valid kernel later. Actually, just raise your hand if this makes sense. Cool. Most of you. So let me just describe a small. So it turns out this let me just describe a couple of quick generalizations to this. One is that if you define kxz to be equal to x transpose z plus c squared. So again, you can compute this kernel in order n time. Then that turns out to correspond to a feature vector where I'm just going to add a few more elements at the bottom, where you add root 2 right. Not sure you read that. That was root 2 cx1, root 2 cx2, root 2 cx3, and c. And so this is a way of creating a feature vector with both the monomial, so meaning the first order terms, as well as the quadratic, all the inner product terms between x1, xi, and xj. And the parameter c here allows you to control the relative weighting between the monomial terms, so the first order terms, and the quadratic terms. Okay, and again, this is still inner product between lengths, vectors of length n squared. You can compute in order n time. More generally, here are some other examples of kernels. Actually, a generalization of the one I described just now would be the following kernel. And so this corresponds to all using all n plus d choose d features of all monomials. Monomials just means the product of xi, xj, xk. This is just all the polynomial terms essentially up to degree d. And n plus d choose d is sort of on the order of n plus d to the power of d. So this grows exponentially in d. This is a very high dimensional feature vector. But again, you can implicitly construct the feature vector and take inner products between them it's a very computationally efficiently, because you just compute the inner product between x and z at c, and you take that real number to the power of d. And by plugging this in as a kernel, you're implicitly working in an extremely high dimensional feature space. Okay. So what I've given is just a few specific examples of how to create kernels. Excuse me, what we're going is just a few specific examples of kernels. So let's ask you more generally, if you're faced with a new machine learning problem, how do you come up with a kernel? So there are many ways to think about it, but here's one intuition that's sort of useful. So given a set of attributes x, you're going to use a feature vector phi of x. And given instead of attribute z, you're going to use an input feature vector phi of z. And so the kernel is computing, the inner product between phi of x and phi of z, right? And so one intuition, and this is a partial intuition that's sort of right, isn't a rigorous intuition that's useful, is that if x and z are very similar, then phi of x and phi of z will be pointing in the same direction, and therefore the inner product would be large. Right? Whereas in contrast, if x and z are very dissimilar, then phi of x and phi of z, may be pointing in different directions, and so the inner product may be small. Okay, that intuition is not a rigorous one, but it's sort of a useful one to think about. And so, if you're faced with a new learning problem, if I give you something, some random thing to classify, and you want to decide how to come up with a kernel, well, one way is to try to come up with a function k of xz that is, let's say, large, if you want the learning algorithm to think of x and z as similar, and small okay, again, this isn't always true, but it's just one of several intuitions. So if you're trying to classify some brand new thing, you're trying to classify, Harrington digits, you're trying to classify DNA sequences or something, just some strange thing you want to classify, one thing you could do is try to come up with a kernel that's large when you want the algorithm to think these are similar and kind of think these are dissimilar. And so this runs in the question of, let's say I have something I want to classify, and let's say I write down a function, right, that I think is a good measure of how similar or dissimilar x and z are for my specific problem. So let's say I write down k of xz equals e to the minus, okay, let's say I write down this function, so z. And I think this is a good measure, right, of how similar x and z are. The question then is this really a valid kernel? So in other words, to understand how we can construct kernels, if I write down a function like that, the question is, does there really exist some phi such that kxz is equal to the inner product? Right? And that's the question of, is K a valid kernel? And it turns out that there is a result that characterizes necessary and sufficient conditions for when the function K that you might choose is a valid kernel. So let me just go ahead and give the intuition. Let me actually go ahead and show part of that result now. Suppose K is a valid kernel. And when I say K is a kernel, what I mean is that there does indeed exist some function phi for which this holds true. Right? Then let any set of points x1 up to xm be given. And let me define a matrix K. And I apologize for overloading notation now. K I'm going to use to denote both the kernel function, which is the function of x and z, as well as a matrix, an m by m matrix. Unfortunately, I don't know. Unfortunately, there aren't enough alphabets, I guess. Well, that's not true. Let me define the kernel matrix to be an m by m matrix such that k subscript ij is equal to the kernel function applied to two of my examples. Okay. Then turns out that for any vector z that's m-dimensional, one should consider z transpose kz. Actually, let's do this on the next board. one should consider Z transpose KZ. And by definition of matrix multiplication, right, this is that. And so Kij is a kernel function between xi and xj, so that must equal to this. Right. I assume that k is a valid kernel function, and so there must exist such a value for phi. This is the inner product between two feature vectors. So let me just make that inner product explicit. I'm going to sum over the elements of this vector. And I'm going to use phi xi subscript k, this to denote the kth element of this vector. Like so. And just rearrange sums. You get sum over k. Right. So this next step may look familiar to some of you, which is just right. And therefore, this is a sum of squares, and it must therefore be greater than or equal to 0. Okay, just do you want to take a minute and look for all the steps and just make sure you buy them all. Yeah. Oh, this is let's see. In this step, this is the inner product between the vector 5xi and 5xj. So the inner product between two vectors is the sum over all the elements of the vectors of the corresponding elements. Oh yes, it is. Yeah, thanks. Yeah. So you're right. This is just A transpose B equals sum over k, AK BK. Right. So that's just this. This is sum of k of the kth elements of this vector. Let's take a look at this and make sure it makes sense. Okay. Do you have questions about this? So just to summarize, what we showed was that for any vector z, Z transpose kz is greater than or equal to 0. And this is one of the standard definitions of a matrix, the matrix K being positive semi-definite. Right? And when the matrix K is positive semi-definite, right, that is K is greater than or equal to 0. Okay? And just to summarize, what we've shown is that if K is a valid kernel, in other words, if K is a function for which there exists some phi such that K of xi xj is the inner product between 5xi and 5xj. So if K is a valid kernel, we showed then that the kernel matrix must be positive semi-definite. Must be positive semi-definite. Okay. It turns out that the converse holds too. And so this gives you a test for whether a function k is a valid kernel. So this is a theorem due to Mercer, and so kernels are sometimes also called Mercer kernels. So it means the same thing, it just means it's a valid kernel. Let k of xz be given. Then K is a valid kernel. In other words, it's a Mercer kernel. I.e., there exists phi such that Kxz equals 5x transpose phi of z. Right? If and only if For any set of m examples, and this really means for any set of endpoints, not necessarily your training set, but just any set of endpoints you might choose, it holds true that the kernel matrix capital K that I defined just now, right, is symmetric, positive, semi-definite. Okay, and so I proved only one direction of this result. I proved that if it's a valid kernel, then K is symmetric, positive, semi-definite. But the converse I didn't show. But it turns out that this is a necessary and a sufficient condition. Okay, and so this gives you a useful test for whether any function that you might want to choose is a kernel. All right. Let's see. Right. And just as a concrete example of something that's clearly not a valid kernel would be if you find a input x such that k of x comma x, if this is -1, for example, then this is an example of something that's clearly not a valid kernel, because -1 cannot possibly be equal to phi of x transpose phi of x, right? And so this would be one of sort of many examples of functions that will fail to meet the conditions of this theorem. Right, because inner products of a vector of itself is always greater than or equal to 0. Okay. Cool. All right. So just to tie this back explicitly to an SVM, let's say to use a support vector machine with a kernel, what you do is you choose some function k of xz, right? And so you can choose, and it turns out that function I wrote down just now, this is indeed a valid kernel. It's called the Gaussian kernel because of similarity to Gaussians. So you choose some kernel function like this, or you may choose x transpose z plus c to the d, etc. Right? So you choose to apply a support vector machine with kernels, you choose one of these functions, and the choice of this will depend on your problem. So it depends on what is a good measure of one or two examples similar and one or two examples different for your problem. And then you go back to our formulation of the support vector machine, and and you have to use the dual formulation, and you then replace everywhere you see these things, you replace it with k of xi comma xj. Okay, and you then run exactly the same support vector machine algorithm, only everywhere you see xi, these inner products replaced with that. And what you've just done is you've taken your support vector machine, and you've taken each of your feature vectors x, and you've replaced it with implicitly a very high dimensional feature vector. It turns out that the Gaussian kernel, this corresponds to a feature vector that's infinite dimensional. But nonetheless, you can run a support vector machine in a finite amount of time, even though you're working with even though you work with infinite dimensional feature vectors, because all you ever need to do is compute these things, and you don't ever need to compute, or you don't ever need to represent these infinite dimensional feature vectors explicitly. And well, why is this a good idea? Well, it turns out, I think I started off talking about support vector machines because I started saying that we want to start to develop nonlinear learning algorithms, right? So here's one useful picture to keep in mind, which is that let's say your original data, I didn't mean to draw that slanted, but let's say you have one-dimensional input data, right? So you just have one feature x and r, is a real number. What a kernel does is the following. It takes your original input data, and maps it to a very high dimensional feature space. And in the case of a Gaussian kernel, it's an infinite dimensional feature space. But for pedagogical reasons, I'll draw 2 dimensions here. Right? So let's say it maps it to a very high dimensional feature space where, you know, like so. So it takes all your data in R1 and maps it to R infinity, say. And then you run support vector machine in this infinite dimensional space or some exponentially high dimensional space, and it'll find the optimal margin classifier. In other words, the classifier that separates your data in this very high dimensional space with the largest possible geometric margin. And in this toy example that I just drew anyway, whereas your data was not linearly separable in your original one-dimensional space, when you map it to this much higher dimensional space, it becomes linearly separable. And so you can use your linear classifier to separate out what's data that's not linearly separable in your original space. And this is what lets support vector machines output nonlinear decision boundaries. And in the entire process, all you ever need to do is solve convex optimization problems. Okay. Cool. Other questions about any of this?
How would you choose the sigma?
Yeah, so sigma is, let's see. Well, I was going to talk about holdout cross-validation later. One way to choose sigma is, save aside a small amount of your data and try different values of sigma and train an SVM using, say, 2/3 of your data, try different values of sigma, then see what works best on a separate holdout cross-validation set, on a separate set that you're testing on. Yeah, it turns out in some of the learning algorithms we talked about, like in locally weighted linear regression 2, you had a bandwidth parameter. So there are a number of parameters to some of these algorithms that you can choose like these by saving aside some data to test on. Talk more about model selection. I'll address this explicitly then. Are there other questions? Yeah.
So how do you know whether moving it up to a high dimensional space is going to give you that kind of separation?
Yeah, right. Great question. So, well, you usually don't know. Usually, you don't know a priori. Sometimes you can know, but in most cases, you won't know a priori that it's actually going to be linearly separable. So the next topic will be L1 norm soft margins, which is what a change to SVMs that works even if the data is not linearly separable. Yeah.
If you can linearly separate it by mapping to a higher dimension, could you also just choose features in that higher dimension and?
Yeah. So right, okay. So it's a question about what to do if you can't separate it in a high dimensional space. So let me try to address that with the discussion of L1 norm soft margin SVMs. Okay. Yeah.
What if you run like like an SVM algorithm that assumes that the data are linearly separable on data that is not actually linearly separable?
Wow, you guys are really giving me a hard time about whether the data is linearly separable. So it turns out this algorithm won't work if the data is not linearly separable, but I'll change that in a second and make it work. So yeah, okay. Before I close this, before I move on to talk about that, let me just say one final word about kernels, which is that. Just one final word about kernels, which is that I talked about kernels in the context of support vector machines, and the idea of kernels was what really made support vector machines a very powerful learning algorithm. Actually, towards the end of today's lecture, if I have time, I'll actually give a couple more cool examples of how to choose kernels as well. But it turns out that the idea of kernels is actually more general than support vector machines, and in particular. We took this SVM algorithm and we derived a dual, and that was what let us write the entire algorithm in terms of inner products like these. Right? It turns out that you can take many of the other algorithms that you've seen in this class. In fact, it turns out you can take most of the linear algorithms we talked about, such as linear regression, logistic regression, even perceptron algorithm. And it turns out you can take all of these algorithms and rewrite them entirely in terms of these inner products. And so if you have any algorithm that you can rewrite in terms of inner products, then that means you can replace it with k of xi, xj, and that means that you can take any of these algorithms and implicitly map the feature vectors, these very high dimensional feature spaces, and have the algorithm still work on them. Okay, so the idea of kernels is perhaps most widely used with support vector machines, but is actually more general than that. And you can take many of the other algorithms that you've seen, and many of the algorithms that we'll see later this quarter as well, and write them in terms of inner products, and thereby kernelize them and apply them to even infinite dimensional feature spaces. Okay. You actually get to play with many of these ideas more in the next problem set, though. Okay, so let's talk about nonlinear decision boundaries, right? And this is the idea of it's called the L1 norm soft margin SVM. Yeah, machine learning people, I don't know, sometimes aren't great at coming up with good names. But here's the idea, right? Let's say I have a data set. Let's see. Right. So this is a linearly separable data set, but what I do if I have a couple of other examples there that makes the data non-linearly separable. And in fact, sometimes even if the data is linearly separable, maybe you might not want to. So for example, this is a very nice data set. It looks like there's a great decision boundary that separates the two classes. Well, what if I have just one outlier, let's say down here, right? I could still linearly separate this data set with something like that, but I'm somehow letting one slightly suspicious example skew my entire decision boundary by a lot, right? And so what I'm going to talk about now is the L1 norm soft margin SVM, which is a slightly modified formulation of the SVM optimization problem that will let us deal with both of these cases. One, what if the data is just not linearly separable? And two, what if maybe you have some examples that maybe you'd rather not get right in the training set. Maybe with an outlier here, maybe you actually prefer to choose that original decision boundary and not try so hard to get that training example right. So here's the formulation. Our SVM primal problem was to minimize 1/2 norm of W squared right. So this is our original problem, and I'm going to modify this by adding the following. In other words, I'm going to add these penalty terms, CIs, and I'm going to demand that each of my training examples be separated with functional margin greater than or equal to 1 minus CI. Right? And you remember, if this is greater than 0, or I think, was it last lecture or 2 lectures ago? I said that if the functional margin is greater than 0, that implies you classified it correctly, right? And if it's less than 0, then you misclassified it. And so by setting some of the CIs to be larger than 1, I can actually have some examples with functional margin negative. And therefore, I'm allowing my algorithm to misclassify some of the examples in the training set. However, I'll encourage the algorithm not to do that by adding to the optimization objective this sort of penalty term that penalizes setting CIs to be large. Okay, and so this is an optimization problem where the parameters are, WB and all of the Cs, all of the CIs, and this is also a convex optimization problem. It turns out that similar to how we worked out the dual of the support vector machine, you can also work out the dual for this optimization problem. So I won't actually do it, but just to show you the steps, right? What you do is you construct the generalized Lagrangian. alpha r. And I'm going to use alpha and r to denote the Lagrange multipliers now, corresponding to this set of constraints that we had previously, and this new set of constraints on the Ci is greater than 0. This gives us a new set of Lagrange multipliers. And so the Lagrangian will be, optimization objective minus sum from 1 plus Ci, right, minus right, and so that's all Lagrangian. Just convex optimization objective minus, or I guess, well, plus alpha times each of these constraints, which should be greater than or equal to 0. And so you can excuse me. So I won't rederive the entire dual again, but it's really, the same math. And when you derive the dual of this optimization problem, and when you simplify, you find that you get the following. You have to maximize W of alpha, which is actually the same as before. And so it turns out when you derive the dual and simplify, it turns out that the only way the dual changes compared to the previous one is that rather than the constraint that the alpha i's are greater than or equal to 0, we now have a constraint that the alphas are between 0 and C. So this derivation is very hard. I encourage you to just go home and try to do it yourself. It's really essentially the same math. And when you simplify, it turns out you can simplify the R's, the R Lagrange multipliers away, and you end up with just these constraints on the alphas. So let's see how I'm doing for time. Okay, I'm going to do this. Just as an aside, I won't bother. I won't derive these either. It turns out that remember I wrote down the KKT conditions right in the last lecture, the Kurush-Kuhn-Tucker conditions for the necessary conditions for something to be an optimal solution to constraint optimization problem. So if you use the KKT conditions, it turns out you can actually derive convergence conditions. So we want to solve this optimization problem. So when do we know the alphas have converged to the global optimum? It turns out you can use the following. It turns out that, right. Yeah, and I don't know. I don't want to say a lot about these. Turns out from the KKT conditions, you can derive these as the convergence conditions for an algorithm that you might choose to use to try to solve the optimization problem in terms of the alphas. Okay. So that's the L1 norm soft margin SVM, and this is the change the algorithm that lets us handle non-linearly separable data sets, as well as sort of single outliers that may still be linearly separable, but you may choose not to separate with a linear discriminant boundary. Okay, cool. So questions about this? Let me clean the board and I'll check if I have questions. Okay, so questions? Okay, cool. Just raise your hand if this stuff makes sense so far. Yeah, okay, cool, thanks. Great. So, the last thing I want to do is talk about an algorithm for actually solving this optimization problem. Right, you know, we wrote down this dual optimization problem with convergence criteria. So let's come up with an efficient algorithm to actually solve this optimization problem. Right? And I want to do this partly to give me an excuse to talk about an algorithm called coordinate ascent, which is kind of useful to do. So what I actually want to do is tell you about an algorithm called coordinate ascent, which is sort of a useful algorithm to know about. And it'll turn out that it won't apply, you know, in the simplest form to this problem, but we'll then be able to modify it slightly, and then it'll give us a very efficient algorithm for solving this SMO optimization problem. And that was the other reason that I had to derive the dual, not only so that we could use kernels, but also so that we can apply an algorithm like the SMO algorithm that I'll talk about in a minute. But first, let's talk about coordinate ascent, which is, you know, just another sort of black box optimization algorithm, I guess. Right. And to describe coordinate ascent, I just want to consider the problem. I just want you to consider the problem if we want to maximize some function w, which is a function of alpha 1 through alpha m, with no constraints. Okay. So for now, forget about the constraint that the alpha i's must be between 0 and c. Forget about the constraint that, you know, sum of yi alpha I must be equal to 0. Then this is the coordinate ascent algorithm. We'll repeat until convergence. We'll do for I equals 1 to m. And the inner loop of coordinate ascent essentially holds all the parameters except alpha I fixed, and then it just maximizes this function with respect to just one of the parameters, with respect to just one alpha I. So let me write that as alpha I gets updated as argmax over, let me write this as alpha I hat of w alpha 1, you know, alpha I minus 1 alpha I hat. Okay. And this is really the fancy way of saying, you know, hold everything except alpha I fixed, and just optimize w, optimize my optimization objective with respect to only alpha I. Right? This is just a fancy way of writing it. And this is coordinate ascent. So one picture that's kind of useful for coordinate ascent is if you imagine you're trying to optimize a quadratic function, maybe it looks like that. Okay, so these are the contours of a quadratic function, and the minimum is here. This is what coordinate ascent would look like. So these are my, actually let me call this alpha 2 and I'll call this alpha 1. My alpha 1, alpha 2 axes. And so let's say I start down here. Then I'm going to begin by minimizing this with respect to alpha 1. So I go there. And then at my new point, I'll minimize with respect to alpha 2. And so I might go to some place like that. And then I'll minimize with respect to alpha 1, with respect to alpha 2, 1, 2, and so on. Okay? So you're always taking these axis-aligned steps to get to try to get to the minimum. It turns out that there's a modification to this. It turns out there are variations of this as well. The way I've described the algorithm, we're always doing this in alternating order. We always optimize with respect to alpha 1, then alpha 2, then alpha 1, then alpha 2. What I'm about to say applies only in higher dimensions, but it turns out if you have a lot of parameters, alpha 1 through alpha m, you may not choose to always visit them in a fixed order. You may have a heuristic to choose which alpha to update next, depending on what you think will allow you to make the most progress. Right? If you have only 2 parameters, then it makes sense to just alternate between them. It doesn't. But if you have high dimensional parameters, then sometimes you may choose to update them in a different order if you think doing so will let you make faster progress towards the minimum, towards the maximum. And it turns out that coordinate ascent is, compared to some of the algorithms we saw previously, compared to, say, Newton's method, coordinate ascent will usually take a lot more steps. Right? But the chief advantage of coordinate ascent, when it works well, is that sometimes your optimization objective W sometimes is very inexpensive to optimize W with respect to any one of your parameters. And so coordinate ascent tends to take many more iterations than, say, Newton's method in order to converge. But it turns out that there are many optimization problems for which it's particularly easy to fix all but one of the parameters and optimize with respect to just that one parameter. And if that's true, then the inner loop of coordinate ascent of optimizing with respect to alpha I can be done very quickly, and coordinate ascent may be a very good algorithm. And it turns out that this will be true when we modify this algorithm a little bit to solve the SVM optimization problem. Okay. Questions about this? Okay. So, all right. So let's go ahead and apply this to our support vector machine dual optimization problem. Right? So it turns out that coordinate ascent in its basic form does not work for the following reason. The reason is with constraints on the alpha i's, right? Namely, well, you recall from what we worked out previously, we have a constraint that sum of yi alpha I must be equal to 0. And so if you fix all the alphas except for 1, then you can't change one alpha without violating this constraint, right? Because if I just try to change alpha 1, well, alpha 1 is actually exactly determined as a function of the other alphas because this was summed to 0. And so the SMO algorithm, which is due to the SMO algorithm, by the way, is due to John Platts, a colleague at Microsoft. The SMO algorithm, therefore, instead of trying to change one alpha at a time, we will try to change 2 alphas at a time. Okay? So, well, this is called the SMO algorithm. In the sense of sequential minimal optimization. And the term minimal refers to the fact that we're sort of choosing the smallest number of alpha i's to change at a time, which in this case we need to change at least 2 at a time. And so then we're going to outline the algorithm. We will select, 2 alphas to change, some alpha I and alpha j via some heuristic. A heuristic just means a rule of thumb, right, in AI and learning. And then we'll hold all the alpha k's fixed except alpha I and alpha j. And optimize, W of alpha with respect to alpha I and alpha j, and subject to all the constraints. Right? And then, well, and it turns out the key step, which I'm going to work out, is this one. Right, of how do you optimize W of alpha with respect to the 2 parameters that you just chose to update and subject to the constraints. Okay. I'll do that in a second. And then you would sort of keep running this algorithm until you have satisfied, say, these convergence criteria up to epsilon. Okay. But what I want to do now is describe how to do this key step, how to optimize W of alpha with respect to alpha I and alpha j. And it turns out that it's because you can do this extremely efficiently that the SMO algorithm works well, that the inner loop of the SMO algorithm can be done extremely efficiently. So it may take a large number of iterations to converge, but each iteration is very cheap. So let's talk about that. So in order to derive that step where we update with respect to alpha I and alpha j, I'm actually going to use alpha 1 and alpha 2 as my example. Okay, so I'm going to update alpha 1 and alpha 2. Right? And in general, this could be any alpha I and alpha j, but just to make my notation on the board easier, I'm going to derive the derivation for alpha 1 and alpha 2. And the general case is sort of completely analogous. And so on every step of the of the algorithm, we'll respect the constraint that sum over I, alpha I, yi is equal to 0. This is one of the constraints we had previously for our dual optimization problem. And this means that alpha 1 y1 plus alpha 2 y2 must be equal to this. Right, which I'm going to denote by zeta. Okay. And so we also have a constraint that the alpha i's must be between 0 and c. Right? We had two constraints on our dual. This was one constraint, this was the other one. And in pictures, let me see. Actually, let me do this on a different board. And so in pictures, the constraint that the alpha i's must be between 0 and c, that's often called the box constraint. And so if I draw alpha 1 and alpha 2, then I have a constraint that, let's see, have a constraint that the values of alpha 1 and alpha 2 must lie within this box that ranges from 0 to c. And so the picture of the algorithm is as follows. I have some constraint that alpha 1 y1 plus alpha 2 y2 must equal to zeta. And it turns out that w, right, so w, oh, well, let me just write this down. And so this implies that alpha 1 must be equal to zeta minus alpha 2 y2 over y1. Right? And so what I want to do is I want to optimize the objective with respect to this, right? And so what I can do is plug in my definition for alpha 1 as a function of alpha 2. And so I have this becomes w of alpha 1 must be equal to zeta minus alpha 2 y2 over y1, comma, alpha 2, comma, alpha 3, and so on. And it turns out that because w is a quadratic function, if you look back to our earlier definition of w, you find there's a quadratic function in all the alphas. It turns out that if you look at this expression for w, and if you view it as just a function of alpha 2, you find that this is a one-dimensional quadratic function of alpha 2 if you hold alpha 3, alpha 4, and so on fixed. And so this can be simplified to some expression of the form a alpha 2 squared plus b alpha 2 plus c, right? Because this is a standard quadratic function. Okay. And this is really easy to optimize. We know how to optimize like from, I don't know, when did we learn this? Was this high school, undergrad calc or something, right? So we know how to optimize quadratic functions like these. So you just do that, and that gives you the optimal value for alpha 2. And the last step is with a box constraint like this. So just in pictures, you know your solution must lie on this line, and so there'll be some sort of quadratic function over this line, say, right? And so if you minimize the quadratic function, maybe you get a value that lies in the box, and if so, then you're done. Or if your quadratic function looks like this, maybe when you optimize your quadratic function, you may end up with a value outside, so you end up with a solution like that. And if that happens, you then clip your solution so that just to map it back inside the box. And that will give you the optimal solution of this quadratic optimization problem subject to your solution, you know, satisfying this box constraint and lying on this straight line. In other words, subject to, I guess, the solution lying on this line segment within the box. Okay. Right, so having solved for alpha 2 this way, you then clip it if necessary to get it back within the box constraint. And then, you know, we have alpha 1 as a function of alpha 2. And this allows you to optimize W with respect to alpha 1 and alpha 2 quickly, subject to all the constraints. And the key step is really this sort of 1D quadratic optimization, which we can do very quickly, which is what makes the inner loop of the SMO algorithm very efficient. Okay. Questions about this? Yeah. Sid?
You mentioned here that we can't change one alpha,
right?
But in the SM algorithm, we can change them 2 at a time.
Right.
So how is that? I didn't understand that.
Oh, okay, right. Let's see. So let's say I want to change. So as I run my optimization algorithm, I have to respect the constraint that sum over I, alpha I, yi must be equal to 0, right? So this is a linear constraint that I didn't have when I was talking about coordinate descent. So suppose I try to change just alpha 1. Then I know that alpha 1 must be equal to, you know, sum from I equals 2 to m alpha I yi divided by y1, right? And so alpha 1 can actually be written exactly as a function of alpha 2, alpha 3, and so on through alpha m. And so if I hold alpha 2, alpha 3, alpha 4 through alpha m fixed, then I can't change alpha 1 because alpha 1 is defined already as a function of these things. Right. Whereas in contrast, if I choose to change alpha 1 and alpha 2 at the same time, then I still have a constraint, and so I know alpha 1 and alpha 2 must satisfy, I guess, that linear constraint. But at least this way, I can change alpha 1 if I also change alpha 2 accordingly to make sure it still satisfies this constraint. Does that make sense? Cool. Any other questions? Yeah.
How do you fix zeta?
Oh, so zeta was defined, someone defined, going to back to this board. So on each iteration, I have, you know, some setting of the parameters, alpha 1, alpha 2, alpha 3, and so on. And I want to change alpha 1 and alpha 2, say. So from the previous iteration, you know, let's say I had not violated the constraint, so that holds true. And so I'm just defining zeta to be equal to this, because alpha 1 y1 plus alpha 2 y2 must be equal to minus sum from I equals 3 to m of that. And so I'm just defining, defining this to be zeta. Cool. Yeah.
So I see in this iteration you use alpha 1, alpha 2. So in the second iteration you use alpha 1, alpha 3.
Yeah, right. So this is so in every iteration you choose maybe a different pair of alphas to update. The way you do this is something I don't want to talk about. I'll say a couple more words about that. But the basic outline of the algorithm is on every iteration of the algorithm, you're going to select some alpha I and alpha j to update, like on this board, right? You select some alpha I and alpha j to update via some heuristic, and then you use the procedure I just described to actually update alpha I and alpha j. Does that make sense? So what I actually just talked about was the procedure to optimize W with respect to alpha I and alpha j. I didn't actually talk about the heuristic for choosing alpha I and alpha j. Okay. All right. Yeah.
What is the function W?
And W is, it's way up there, I'll just write it again. W of alpha is that function we had previously, right? W of alpha was the sum over I, you know. So all this is about solving the, right, it was that thing. Right, so all this is about solving the optimization problem for the SVM. So this is the objective function we had, so that's W of alpha. Okay, yeah, this last question?
In changing one of the alphas, you change another one that works, right?
Say that again?
In changing one of the alphas, optimizing that one, you can make the other one that you have to change worse, right?
That works? What do you mean works?
Worse. So
worse.
It will get farther from its optimal.
I see. Yeah, let me try to say it differently. So what we're trying to do is we're trying to optimize the objective function W of alpha. So the metric of progress that we care about is whether W of alpha is getting better on every iteration. And so what is true for coordinate ascent and for SMO is that on every iteration, W of alpha can only increase. It may stay the same or it may increase. It can't get worse. It's true that eventually the alphas will converge to some value. It's true that in intervening iterations, one of the alphas may move further away and then closer and further and closer to its final value. But what we sort of worry more about, what we really care about, is that W of alpha is getting better every time, which is true. Okay, cool. So, all right. So just a couple more words on SMO before I wrap up on this. One is that there's usually heuristic. John Platt's original algorithm talks about the heuristic for choosing which values, for choosing which pair alpha I and alpha j to update next. It was a fairly complicated heuristic. Is one of those things that's sort of not conceptually complicated, but it's very complicated to explain in words. So I won't talk about that here. If you want to learn about it, go and look up John Platt's paper on the SMO algorithm. The heuristic is really pretty easy to read. And later on, we're also posting a handout on the course homepage with sort of a simplified version of this heuristic that you can go and implement using the problem set or whatever. Okay. So you can see some of the classes readings for more details. One other thing that I didn't talk about was how to update the parameter b, right? So this is solving all your alphas. This solves to the alphas. This allows you to get w. The other thing I didn't talk about was how to compute the parameter b, and it turns out that's again not very difficult. But I'll let you read about that yourself with the notes that we'll post that we'll post along with the next problem set. Okay. So to wrap up today's lecture, what I want to do is just tell you briefly about a couple of examples of applications of SVMs. I lost track of. Right, let's try to go in order. So let's see. Let's consider a problem of handwritten digit recognition. Right. So in handwritten digit recognition, you're given a pixel array, like a OCR, or excuse me, like a scanned image of say a zip code someone may have written. And so this is an array of pixels, and some of these pixels will be on and other pixels will be off. And this combination of pixels being on maybe represents a character 1. Right? And so the question is, given an input feature vector like this, if you have if you have say 10 pixels by 10 pixels, then you have say a 100-dimensional feature vector. Right. Number 100 is not actually accurate, but if you have 10 pixels by 10 pixels, you have 100 features, and maybe these are binary features of x being 0 or 1, or maybe the x's are grayscale values corresponding to how dark each of these pixels was. so how do you build a handwritten digit recognizer? Turns out for many years there was a neural network that was the champion. There was a champion algorithm for handwritten digit recognition. And it turns out that you can apply an SVM with the following kernel. It turns out either the polynomial kernel or the Gaussian kernel works fine for this problem. And just by writing down this kernel and throwing an SVM at it, an SVM gave performance comparable to the very best neural networks. And this is surprising because the best neural networks, this is surprising because the support vector machine doesn't take into account any knowledge about the pixels. And in particular, it doesn't know that this pixel is next to that pixel. And so, because it's just representing the pixel intensity values as a vector, right? And so this means that performance of SVM would be the same even if you were to shuffle all the pixels around. But with an off-the-shelf algorithm like this, it was let's say comparable to the very best neural networks, which had been, sort of under very careful development for many years, I guess. Let's see. I'm going to tell you about one of the cool example, which is SVMs are often used also to classify other fairly esoteric objects. So for example, let's say you want to classify protein sequences into, I don't know, different classes of proteins. Every time I do this, I suspect the biologists in the room cringe, so I apologize for that. But getting all my biology wrong, I guess. So there are 20 amino acids, and proteins in our bodies are made up by sequences of amino acids. And even though there are 20 amino acids and 26 alphabets, I'm going to denote amino acids via the alphabets A through Z, with apology to the biologists. And so a typical protein sequence may be, actually let's do it on a different board. And so, here's an amino acid sequence represented by a sequence of alphabets. Whatever, right? Random sequence of alphabets. And so, suppose I want to assign one of this protein into a few classes, depending on what type of protein it is. The question is, how do I construct my feature vector? And so this is challenging for many reasons, one of which is that protein sequences can be of different lengths, right? So there's some very long protein sequences and some really short ones. And so you can't have a feature saying, what is the amino acid in the 100th position? Because, well, maybe there is no 100th position in this protein sequence. There's some very long, some very short. So here's one feature representation, which is I'm going to write down all possible combinations of, say, 4 alphabets. So I'm going to write down AAA, AAB, AAC, down to AAAZ, and then AABA, and so on, right? You get the idea. Somewhere I'll have BAJT. Okay, and then write down all possible combinations of 4 alphabets. And my feature representation will be, I'm going to scan through the sequence of amino acids and count how often each of these subsequences occur. So for example, BAJT occurs twice, and so I'll put a 2 there. And none of these sequences occur, so I'll put zeros there. I guess I have a 1 here and a 0 there, say. Okay? And so this very long vector will be my feature representation for a protein. Right? And this representation applies no matter how long my protein sequence is, right? So how large is this? Well, turns out this is going to be in, R 20 to the 4. And so you have a 160,000 dimensional feature vector, which is reasonably large even by modern computer standards. And clearly we don't want to explicitly represent these high dimensional feature vectors, right? Imagine you have 1,000 examples and you store this as double precision floating point. This, even on modern day computers, this is big. But it turns out that there's an efficient dynamic programming algorithm that can efficiently compute inner products between these feature vectors. And so you can apply this feature representation, even though it's a ridiculously high dimensional feature vector, to classify protein sequences. I won't talk about the dynamic programming algorithm. If any of you, have seen the Knuth-Morris-Pratt algorithm for finding subsequences, it's kind of reminiscent of that. But you can look this up if you're interested. So this is just another example of a cool kernel. And more generally, if you're faced with some new machine learning problem, sometimes you can choose a standard kernel like a Gaussian kernel, and sometimes sometimes actually research papers written on how to come up with a new kernel for a new problem. Okay, just two last sentences I want to say is, so where are we now, right? That wraps up SVMs, which many people would consider, one of the most effective off-the-shelf learning algorithms. And so as of today, you've actually seen a lot of learning algorithms, and so I want to close this class by saying congrats, you're now well qualified to actually go and apply learning algorithms to a lot of problems. But we're still in week 4 of the quarter, so there's more to come. And in particular, what I want to do next is talk about how to really understand the learning algorithms and when they work well and when they work poorly, and to take the tools which you now have and really talk about how you can use them really well. So we'll start to do that in the next lecture. Okay, thanks.